So today I'm going to talk about more on processing and specifically on casting. Last time I gave a general overview and I mentioned that solidification and segregation is something we're going to cover in more detail, so that's today. And I'm also going to give you examples of specific technologies that are used for casting parts that are used as is. Tomorrow and Wednesday, Professor Eager is going to continue the material selection portion of the class, and we'll meet again on Thursday. And on Thursday, what we'll do is essentially take castings and process them by rolling and working to make wrought products. And we'll talk a little bit about forming. So that's the outline for today and the week, actually. Does everybody receive the email? Because I sent one over the weekend. If you're not on the list, again, just let me know. Send me an email and I'll add you to the class website. So we talked last time about when you cast, you have the skin essentially that is being cooled and solidified more quickly. And then a lot of times you have these columnar grains, and I've shown you some images of dendrites and stuff. And then in the center, it cools down and solidifies more of a regular structure. And I showed this relatively quickly about the effect of heat transfer and nucleation. We're going to talk more about nucleation today because it's like forming ice when you solidify a metal. So it takes some time to start the crystals, and then from the time you start it, the crystal is going to grow. It's not instantaneous, and if it would, it will essentially start the solidification at surfaces, and that comes across a lot in polymers. If you are solidifying polymers, semi-crystalline polymers like polyethylene, polypropylene, you can add particles that will act as nucleation sites, and that's a little bit how you distribute and control how many nucleation sites you're going to have. In the example I gave last Friday, it was the roughness of the surface because the solidification was starting from the surface. But in a polymer in general, you can essentially say, oh, I want try to have as many initiation sites to end up with a very fine structure, and you work around that by adding particles essentially to your melt. So it can be useful. You can essentially make use of a lot of the natural phenomena, but what we're going to focus on for the next 15-20 minutes is what exactly is happening when I take the molten metal and I cool it down to solidify it to form a solid. So this book here from Porter and E. Sterling is, I think, the right level for both undergraduate and grad student, because it doesn't spend a whole lot of time. It's actually on different phase transformation, and I'll come back to it when we talk about heat treatment. It's not this thick just talking about solidification, or it's not 2-3 pages, it's a chapter. So, and I'll use a lot of demonstrative from that. So what happens, and we talked about that last time, we said in order to solidify, we need to be reducing the free energy. So the free energy is that delta G, and it's a combination of the internal energy and the entropy of disorder. So when you solidify, you're varying both. One is more related to the organization, one is more related to the internal energy, the bonding between the atoms. There will be a point where, so let's say for fusion here, for fusion. So there will be a point where in the ideal world, if you take that general equation, you would want to transfer from a solid to a liquid. No, the other way around, sorry, from a liquid to a solid. The problem is, how is it going to happen? because it's very different to be a solid and to be a liquid. When you're a solid, you organize as crystals. When you're liquid, everything moves around and it's the same composition. So what I'm showing here is what happens to that internal energy when you try to introduce, say we have a large volume of liquid, and then you try to introduce a little solid in it, and I'll put it as, you know, crystal. You create surfaces. Now you have interfacial energy between the two substances. And from, you know, all I can remember from when I was learning like you guys, it's something that is a little intuitive, but at the same time, it's good to come back to it whenever you feel like, oh, you know, why is this so time sensitive? If I pull really fast, I will start forming these solids portions at a lower temperature, because I don't give it the time to just come by. So that's what we call thermal activation, things that will happen randomly every once in a while. So every once in a while in the liquid, you'll have something that looks organized, and the question is whether it's going to disappear or grow. There will always be a little area, oops, you know, all of a sudden the entropy is going down, the atoms are getting closer, and the question is this the lowest state energy or not? And then it will fluctuate backward, or it will continue to grow. So what I'm showing here is there's a critical radius here, so I'll put the R on that one, the R star, where the interfacial energy is becoming less important. And overall, it's less energy to continue growing the solid than to essentially dissolve it back. And that state where we have the R star is not really a reduction in free energy. If you see it, it's just it's the upper point where you have essentially you can go backward or go forward. And that's a quantity that you can think of when you're trying to say, okay, so if I have a lower temperature, and that's shown in some of these graphs, it's going to require less of a driving force. This tends to move to a smaller radius at a lower temperature, but it doesn't come as often because you have less thermal activation. So the vibration in the atoms keeps going down as you reduce the temperature. So you want to try to avoid being in this situation where, well, unless you want to, where all of a sudden the driving force is very high in terms of thermodynamic, but things can't move anymore. It's kind of tooling. And that's a way to, if you have very sophisticated chemistry, you can form amorphous metals by cooling them more quickly, because you get to a temperature that's low enough that they cannot organize and form this crystallized structure. I would say though that if you deform some of these amorphous metals, or we call them bulk metallic classes, they will form some crystals, because the deformation essentially activates the movement of the atoms and help them get back to where they want to be in terms of equilibrium. So this is a general concept, but it ends up being helpful in our context for solidification, thinking that even though I reach the critical temperature where this equation says it's 0, then I need a way to go from the liquid to the solid, and that's by forming this nucleus there. If you had to form this nucleus just like I drew, I'm putting on the board here the kind of temperature that you'll have to be below what we consider the fusion temperature. So we take the fusion temperature as when this equation becomes negative. You want to have the solidification. So from that temperature, if you're looking at steel, you would only form these crystals about 300 degrees below. Yes?
I know that in monocrystalline wafers, they just put a single ceramic crystal and shows the
Yes, yes. So if you have something to begin with, and that's my next slide, you will essentially eliminate the need of forming it on the first place. So by the time that you have something to start your crystal, and it doesn't have to be necessarily another crystal, it can be an impurity as well. You're reducing this, and you can reduce it to pretty much 1 degree or 10 degrees, depending on the temperature that you're dealing at. So that's where it becomes important to understand that this equation is not taking into account the kinetic, the formation process. So there are two ways to go around it. It's either you already have a crystal, and all you need to do is to grow it, a crystal that's big enough, or you have little impurities, and that's what happens when you have roughness in your mold. Is you will still, if you just start forming a solid in a groove here, you still have an interface between your solid and the mold, for example, but that interface is essentially replacing the liquid to the mold interface. So it may not be a big deal at all, it may just be an equivalent. And by doing so, you're really reducing the volume of that natural phenomena here. You only form a solid in a very, very small area, but it'd be stable because it's stabilized by that interface with the mold. The only thing that the image in D shows is it's true that you can start it in a cavity, but this example shows that eventually you'll reach the main surface here, and sometimes it may stop right there. You know, it depends on how exactly is your temperature and what is the energy for changing the interface here from the liquid to the mold to between two solids. And that depends on the quality of contact, if you have a metallic mold, if you have a ceramic mold, a sand mold. So there's a lot of variation. Your idea about using another crystal is, by far the least amount of energy, because you just literally continue adding to the same structure. So it will happen exactly at this temperature, and if you do it slow enough, you can prevent other sites, including little impurities and imperfections in your containing system, so you keep growing that one grain. But if you decide to cool it a little too fast, you may start forming other grains at other locations, and then all of a sudden you have a polycrystal. So it's very delicate to form single crystals. You have to take the time it takes. And that may be the right time to introduce the example of a turbine blade. What you do with a turbine blade, if you want to use it at very high temperature, and it needs to be metallic. So one reason for having it metallic is it will be able to withstand higher temperature and it still have a good fracture toughness. So you gain the fracture toughness by making it a metal as opposed to an intermetallic or a ceramic composite. But you'll have creep at high temperatures. So the way to design out creep is to make it a single crystal. It doesn't eliminate creep, but it reduces it. And for our casting purpose here, one way to make the single crystal is, say I have the mold here, but I'm going to have a blade. Not even gonna try, make it complicated. I can essentially have my mold that I fill with liquid, and then I create a little spiral effect that feeds right into it. So I put all of this at high temperature under a vacuum, all the conditions that I want so I don't oxidize my metal. And then I'm going to start cooling this phase, and it's funneling down. So this is actually a tube, not just a wire. So say I start right here. I'm forming a bunch of crystal. and actually need a little more space here, but that's still fine. And the crystal that's going to go the faster is going to start engaging in that spiral. And by the time I'm done with the spiral, I only have one grain. The weather grain, which is the one that maximizes the heat extraction, so the thermal transfer, and it's also well oriented for stacking purposes. Yes? Here's the spiral. Thank you, Professor Eager. So the working part is on top here, and you still, actually, maybe, I'm not sure.
You can't see it, they haven't been etched.
Yeah. If you could etch this to see the different grains at the bottom, but we don't see it here. This only shows the general idea. So that's the other extreme here, where you actually, it's on purpose. You try to go as slow as possible, so you don't have up here all of a sudden one grain showing up. We talked last time about segregation, and I think I mentioned to you that it was related to the phase diagram, so we're just going to go in more details with that now. Most of the time we don't deal with pure metals, and we sometimes deal with pure eutectics, so something that will go from the liquid to the solid at a very specific temperature. But most of the time, we have some alloying element that have a reduced solubility in the solid. So the solid is this line here. This is just a simple binary phase diagram. So over here, all we have is solid. Over here, we have the liquid. And in between, we have these two zones. So if you start with a nominal composition, the graph has it as x0. That's what you put in the furnace. And even if you cool it down very, very slowly, what's going to happen at this temperature, well, they have this example here, so we can use that. But starting here, you'll form solid with this composition, as opposed to the nominal composition. So all of a sudden, you have a different composition in what you are solidifying and what is your liquid. And that's where we talked about the diffusion and essentially taking the alloying elements and pushing them forward from their solidification front. And that's where I started talking about, well, it's easy to form dendrites then, because you sort of accumulating things right ahead, and then you want to side branch it and find other ways to solidify that are more favorable in terms of kinetics. But this here is still, regardless of the time that you take, even probably it's fair to say the slower you go, the more it's going to segregate here, because you start with that composition here, and it's not going to change after the fact because it's very slow to diffuse into the solid as opposed to the liquid. So what happens is the liquid composition keeps creeping up. It starts here, it goes higher, keeps going higher. And that's, again, all based on thermodynamics. It doesn't give consideration into kinetics. So again, one way to avoid it is to pick that composition, because you're going to go straight from a liquid to a solid. But there are a lot of conditions where these alloying elements are very helpful in terms of improving mechanical properties. That's the reason why we use them. All the aluminum alloys, we make advantage of here the reduced solubility to form precipitates that increase the strength. So what is the disadvantage in terms of making the alloy is the main advantage after the fact when you're trying to improve the properties. So we have to do it. And we have to work around the physics here with the thermodynamic stability of the different phases. So this will happen. In this example, it's two-dimensional. So when we see here that the bar composition looks like this, it's assuming you're not forming the dendrites. But even without dendrites, you have segregation, and that's the point I was really trying to make with you guys. Now, about forming dendrites. that's here, you know, the most abstract theory probably for today's class, so bear with me for 1 second. We are located here. We already form a solid, and now we're looking into solidifying more solid. What happens is, at the very interface from the solid to the liquid here, there's a lot of diffusion in the liquid. It's fair to say we are in equilibrium. We don't have a significant offset from equilibrium. So that's why here we're putting this point here at the temperature here is the temperature of fusion for this exact composition because the composition keeps changing. If you move ahead here, you can have a situation so the thermal gradient, that's the temperature of the liquid here, tells you is based on heat transfer. So we're putting it here as a straight line. The heat keeps going towards the mole, and we assume we're in quasi-steady state. So it's not too bad of an approximation. At the same time, what we have here is the temperature of equilibrium for that solidification process. So what you find here is that you are far below, so this is the temperature where this composition will start to solidify, but you're actually at this temperature, so now you have an offset when you are located ahead of your solidification front. And that's what leads to this directionality in the formation of dendrites. And sometimes you can also start forming other crystals ahead if you're fast enough in your cooling rate. So it's a competition between the thermal transfer and the composition transfer, and that's the one we're showing here. So because there are more elements close here to the front, the temperature of solidification is lower. So we're all looking very close here to this interface. We're not looking all the way to the end of the alloy. It's not the easiest, but it's the most complete explanation, I would say, about why we have an unstable solidification front. So they call it constitutional supercooling. Supercooling just means that you are at a temperature below your fusion temperature for that composition. It's very common to have some supercooling when we go through solidification, but not the 200 or 300 degrees that we talked about if we had to do it with our single crystal here. That would be 200-300. If you go really slow and you're doing silicon, maybe a degree. A typical case is, say, 10 degrees or so is typical. If you're casting, and that's where we're going, you end up heating your metal above the fusion temperature. And that one we call it the superheat. Everything is super. So superheat is the temperature above the melting point of the alloy. It accounts for some temperature decrease by the contact with the mold as you're feeding your liquid metal. So this is an example here of just a general casting process where you have your molten metal here from the underneath and you're feeding it up. The advantage of this is you're in a more controlled condition. And I don't want to show it necessarily in chronological order of complexity. So here I'm showing you an example where you don't worry about gravity effects splashing from having tried to control the liquid at high speed. This is happening very slowly from the bottom to the top, and you essentially have an exit path for your gas. So the problem when you try to pour in the bowl is there's already something there. There's air or there's a gas unless you've thrown it under vacuum ahead of time. So for casting, you need a mold, and here what you have is, in this view, we see at least 8 parts being done at the same time. So you have a riser, and you're screwing your system to distribute that liquid metal into the parts that you want. It's the most typical way of doing it. And after you're done, The way this set up here, you can either open the mold if it's a permanent mold, or you break it if it's a consumable. So we're gonna go into more details of this. It's kind of the sequence here where you have to make your mold. That's an important part. Sometimes humidity in your mold will create a lot of imperfection, porosity. So the making of the mold is very important. We had a project that lasted just about a year with Tiffany, the jewelry maker, and it was very interesting because it was relatively conventional, old school metallurgy that they were doing. They're casting a lot of platinum for making rings, and they have these prong settings and all that. It's not completely machined off a block of platinum. There'd be a lot more money to get the whole block of platinum machined down. They obviously recover everything, so even like when they're polishing, they use screens to collect back the platinum and reuse it. But I'm bringing it up here because, and as part of our review, we essentially concluded that, well, first of all, making molds for platinum is not easy because it melts at a high temperature. So you need a mold that can resist higher temperature than most other metals that we cast. I mean, one of the easiest is aluminum. It's relatively lower temperature. You can use permanent molds, but here at those temperature range, you almost have to go with consumable molds, and you come into entrapped air or entrapped moisture, and a lot of things you're trying to eliminate, and still have enough ductility so it doesn't break. A good surface finish, because we've just talked about how it's affecting the quality of the part, the quality of the contact between the mold and the metal. So that was one area that there isn't that much going on just for melting it. But in terms of protecting it from the environment, do I need to use vacuum or shielding gas? Is it okay to use air? That's a lot where the different, that's where the expertise comes in, to put it this way. I decided to introduce this here, well, we're a little past the middle of the class, because I talk about different things and I'm using different references, but there is a material science website as part of MIT, and it's giving you, very useful link. There's a link here to the ASM handbooks online. That's a series of 30 handbooks, each about this thick. On material science, casting, heat treatment. When you're looking for something very specific for a project, say you want to know about titanium alloys, what are the typical composition, you can obviously do a Google search, but this will get you into a chapter that specifically talks about it. It gives the introduction and data. So the ASM handbooks, I point to them in particular because they have a lot of data. It's not necessarily the best place to really understand solidification, but by the time you know about it, if you want to know more about a specific process or a list of processes, it will be there in the different volumes again. You can go as many details as you want. So, sand casting, there's a chapter in the ASM handbook about it, but actually you didn't use that image. So. You make a pattern of your part, and you can keep it. You can keep reusing it. So that's this little box here, the blue box. And you throw it in sand, or you essentially impress it in something, and you cure that something. It could be sand with a binder, until you have a part. Now you reopen it. So after you cure it, you reopen it to take your part off. Close it back, and you use that for casting. When you're done casting, your consumable generally is gone because it went through such a thermal cycle when you pour the liquid metal into it. Plus, you need to get your part off. So in the end, you separate everything. Realize now we're setting all the final processes. But it's not a very advanced process. It's relatively inexpensive. The mold material costs nothing. And you can do batches and make these trees that are shown in one of the initial images. I'm showing here a fitting for a piping system because it's one of the large users in terms of quantity. So you have cast iron and you have malleable iron. One is brittle. And I remember reading a description of a building code saying one of the reasons for using cast iron, and I should go back to that quote, was if there's a fire, you can hammer the fittings and you'll get water out so you can, to throw the fire off. It's crazy. It doesn't make any sense, I think, in modern world because we got fire sprinklers everywhere. If there's water in the building, you just go away. You don't try to hammer down, But it's probably something that somebody said 100 years ago and nobody decided to, correct it. We invented fire sprinklers, just happened between then and now. So there is no reason for using a brittle material like a regular cast iron other than cost. It's pretty much the cheapest metal you can find because it will come to the shape you want, and you can see here you even have the markers included with your casting. And this example I picked because you can see that the flanges are being machined, so you get a good fit at those locations. So there would be situation. It's very typical. You go to Home Depot or Lowe's, you look at the fittings, and you can say, oh yeah, it's a little rough. It's a casting surface, and then you have the machine tread coming into it because casting treads will not give you a good fit. It will not give you the best properties either. So that's essentially what I wanted to say here about sand casting. The jewelry stuff, you can see here in more details this riser and the different parts as a mold. The difference here is it's so intricate if you look at that left side image that you can't expect to be able to recover your pattern. I talked about the sand casting as if you put it in, you get your stuff set, you take it off, and then you cure your whole mold. Here you lose it, and that's why we call it investment. You invest in your pattern and you're going to have to make another pattern the next time around. So that's the reason of the word investment casting or lost wax. Everything else is relatively the same, so you can sculpture these wax pattern or you can have molds to make the wax pattern and as a permanent mold that you just fill, make the wax, open it up, and then you assemble it. So here you can use you can essentially fuse the wax and make the geometry that you want, and then you essentially pour it in slurries that different composition depending on what's the temperature. If you're doing silver, it's very easy because you don't have to go to high temperature. If you're doing platinum, there are only very few recipes that will allow you here to make the mold out of this. You heat it up to get the wax out, and then you pour your metal. So if you remember, investment is because you lose the pattern. That's the main difference between a sand casting and investment casting or lost wax. Centrifugal casting is something that is used in jewelry. And one of the advantage obviously is it's fast, because if you're looking, there's a drive here, there are different ways of doing it, but the way I've seen is, say the axis of the whole centrifugal machine would be right here. So off center you have your molten metal that you can pour into it's your riser system, and it gets injected into your parts. So one advantage is you don't really need a pressure system and pistons in a very complex way for feeding the metal like we've shown in this schematic. You just start spinning, and eventually the molten metal gets off your little crucible here and gets distributed. My experience has been that you don't really control how fast it goes out either. So I see more issues with this than advantages in terms of controlling how fast the liquid is going to be flowing. I'm sure there are ways to do it right, but it's just a lot more optimization in terms of controlling the flow of the metal coming out. And if you want to talk about Tiffany, we'll do it outside the class. Die casting. So I'm taking a completely different turn here. I want to talk about a process that is more like a press. So you, instead of coming and taking your pattern, making one mold, then going to the slurry and making the mold for casting and then pouring into it, breaking it, and working with the finish. This process takes the liquid, injects it in a permanent mold, and you form the part right away. So it's great for aluminum or relatively low melting point alloy. It's also great when you have large volume because there's a lot of cost in terms of developing the whole feed system. If we're talking about a metallic mold, it's great because it will cool down faster than when you have a ceramic or a sand mold. But at the same time, it's not as forgiving for mistakes. You can end up completely solidifying in one of your riser and you don't get anything, you don't get a complete part. Or you can get more porosity. It's just a much faster process. So it needs a lot of design to happen and make good parts. It is used for aluminum wheels and a little bit for the same reason as the jewelry is you don't have to use a big disc of aluminum and then start machining it off to very small thicknesses. Yes?
Can you alloy so?
Oh yeah, you have to use alloys to essentially, well, for mechanical properties, if we use pure aluminum, it'd be such a low strength that it'd be a big problem. The other aspect is it reduces your fusion temperature, which